Leetcode 191, number of 1 bits. It's an easy problem, but of course it's only easy if you are well versed in bitwise operations. And here is the description. Given a positive integer n, and that's our input integer called n, write a function that returns the number of set bits. Yeah, and of course, in a binary representation of any number, we have digits, which can be only 0 or 1, and those are called bits. And we have to count the number of those digits which are ones. So how many ones are in this binary representation? If we check here, a set bit refers to a bit in the binary representation of a number that has a value of 1. And it's also known as Hamming weight. So there's a Wikipedia article on it, but you can already see examples here on the right side. It's basically the number of ones in the binary representation. And we have following examples, but just before we go into it, let's see the constraints. And the constraints are the following, meaning that the number will be always up to 32 bits, because it's less than 2 to the power of 31, meaning that it will be an unsigned, because it's always positive integer, 32-bit number, which is something which we will use later on, but just keep it in mind for now, and let's take a look at the examples. And of course, the examples don't tell us much more than we have already said. If you have number 11, it will be represented in binary as such number. It has 3 ones inside, meaning that the output is 3, and the following number has just 1 in its binary representation, and that's the output. And this number has almost all ones, and the output is 30. And that's it. So now let's think about what kind of potential solution we might come up with. And we will discuss 2. Let's maybe use this. Let's use this example and its binary representation. And of course, there are in total 3 ones here, meaning that the result is 3. Let's move it a bit here. And there are a couple ways in which we can solve it, and we will need some bitwise operations for this. Mainly shifts, and we will only use shift to the right. By 1, which is also equivalent to division by 2. If you shift following number to the right, what will you get? Shifting by 1, you are getting, let's say, the following scenario, and there's a 0 that pops from the front, and the last digit goes outside of boundaries and gets removed. That's shift by 1. To the right. This, and we can repeat it multiple times. And how many times would be what would be the maximum number of shifts we can use? It depends on how big the number is initially. because at some point we will arrive at 0, and then we can still keep on shifting, but the number will not change. And because we said that it's a 32-bit unsigned integer, that means that we can do at most 32 divisions. But that would be it. And each time we shift, we lose the last digit or the lowest digit. And we can simultaneously do another operation, which is bitwise AND. And what do we get from bitwise AND? We can get the number which is the last digit, of course, before the shift. Yeah. So if we do the bitwise AND, then what happens? And 1, between this number and 1. Yeah, then the result is the last digit, because we simply check what is the result of the following operation. 1 and 1. Yeah, and of course 1 and 1 gives 1. And like you can think about this also in a logic related way. True and true gives true. And the only other option is 1 and 0, which gives 0. Yeah, so that's how you can extract the last or the lowest digit. And if we repeat it multiple times, then you can see in each iteration we will be getting the last digits, and this time it's also 1. Then we have following, which will have 0, and then 1 again. Yeah? And each time we can do it in a loop up until we have nothing left, up until there is a number here which is greater than 0, so while n. And each time we can extract the last digit and count how many ones we have. Yeah, so let's try to do it in Python and store the result in an additional variable. Yeah, so basically those extractions we will be adding to this result. And while there is still something here, we can add to the result the result of this operation, and then shift to the right n by 1, yeah, which is the same as dividing it using integer division by 2. And we can return the result. At the end, which is everything that we need to have, that would be like our first solution. And let's see how fast we are. And of course, we beat everyone, because this, normally when we have something like this in programming, we will say that it's log n time complexity. Why log n? Because each time we divide the number by 2. That's why it's not on, it's log n time complexity. But is it really log n? In fact, because we know for sure, let's see the description, that the number is from this range, we can have at most 32 divisions. Yeah, we will never have more than 32 divisions. That's why we can also think about it in O1 terms. Yeah, but there is one additional option which I wanted to show you. We could pre-compute in case of this problem doesn't make sense, but theoretically we could do it. So we can store it in some additional variable, and we can pre-compute the results, since they ask here follow up if this function is called many times, how would you optimize it? Yeah, and we could do this computation, which will be done only once, and then we can use it as hash and only read the results from here. So we can convert string, or we can convert to binary for I in range 8. 2 to the power of 8, which we will do this cache for every 8-bit number. Yeah, and then we can divide any 32-bit number into 4 8-bit numbers. And we can simply count number of ones in range. Yeah, and then of course we can do it outside. You have to do it only once for a given class, and then we will store the results in some form of a cache. Yeah, and each 8-bit number, let's show it on this example. Here you can basically subdivide it to each 32-bit number to 4 8-bit numbers. And that would be one way to do it. Of course, you can also subdivide it to 4-bit numbers and so on. Yeah, but I think that would be enough. 1, 2, 3, 4, 5, 6, 7, 8. And that would be first bucket. Then the next bucket. 1, 2, 3, 4, 5, 6, 7, 8. What's wrong to here? And then 1, 2, 3, 4, 5, 6, 7, 8. And the last one is here. And we have 8 bits. 8 bits. And this can be done for each 32-bit number. And then we already pre-computed all the combinations for all possible 8-bit numbers in our cache here. And we can simply just add the result would be sum of those results for each sub part. So how do we get the first part? We get it using pop count and we can add a mask, yeah, to clear everything besides given part. Yeah, so we want to remove everything, and that would be the first part. Then the second. How do we get the second part? We simply shift by 8. And then we shift by 16 and 24. And we can access it through self. Let's see. And you forgot a comma. In range, sorry. Like this. Well, syntax, let me just put them all on a single line. And of course, not shift to the left, shift to the right. Want to divide and move them. So the first one, you shift this number to the left by 8. And then what do you get? You simply remove the 8 digits from this side. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Get 8 zeros from this side. 1, 2, 3, 4, 5, 6, 7, 8. That's the result. Yeah, and then you do the mask to remove everything besides the last 8 numbers, 8 digits. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, and this is done using that mask. And because what's this number? Those are just those 8 ones in binary representation. Yeah, so this is 255, I think. Okay. And let's check. Here, yeah, sorry, that's not how we do the power in Python. And so it's to do the 8th power, and it was my mistake. Some other languages represents power in this way, but not Python. Okay, submit. And we are still beating everyone, but this theoretically could be a more optimized solution if it's called multiple times.